Hello, everyone. We're going to be looking at essentially how hooks work in PyTorch. So PyTorch hooks are kind of an important part, I realized when I was writing this course on distributed training, especially like with how things work from the ground up, because hooks are very powerful when it comes to sort of modifying how model behavior changes during training and even during inference. And on top of that, it powers a lot of the technology that you might not even realize. So today I'm going to go over what the four kinds of hooks are, how you write hooks in the first place, what they're useful for, and then we'll end up in a classical example, as you can see, essentially recreating a very, we'll call it low-tech version of Accelerate's big model inference, because it's all actually through hooks. If you have questions, please put it in the chat. I will be keeping an eye on it, and I'll go over questions during pauses when it makes sense. So, first, there are four kinds of hooks. The first one is what we call a pre-forward hook. The second is what we call a forward hook. The third is a backward hook. And the fourth is registering hooks on tensors themselves. Now, what is a hook, though? Without explicitly giving us the answers of what these kinds are, essentially a hook is a function that modifies an input or a set of inputs or a particular state during some part of the forward pass and back propagation cycle in a neural network or as part of a tensor when it's called, for instance. So the pre-forward hook, the namings for PyTorch hooks are a little weird. Pre-forward hook means it happens before the forward pass. So before we have an input that goes through the layers. The second one is what we call the forward hook, which this happens after the layer execution, which is why I find it a bit confusing, because it's like, well, a forward hook, I would expect it to call before the forward or during, but it's pre means before, without the suffix means after. So forward hook happens after we run an input through the layer via the forward pass. Backward hook happens after we calculate the gradients and perform backpropagation. And then register hook on a tensor is called when the gradients are computed for that specific tensor during backpropagation. So essentially it allows you to inspect or modify the gradients as they're being calculated. Matei threw in chat, who also works on Accelerate. You can also register hooks on optimizers. Let's pull up his documentation here. So on an optimizer, in this example, we have register load state dict pre-hook, which, as the name implies, gets called before we call load state. Fascinating. PyTorch has all these hooks, and each of them are useful for different things. I would love to see an example of how this can be useful. I have a few ideas probably related to FSDP and distributed state dictionaries, and loading them in would be my best guesstimate and where my hunch sort of would go to. And there we go. I am exactly right. Now, what are some general use cases for hooks? I've got two examples hidden there, but let's sort of think about it conceptually. So we have methods for modifying chunks of either inputs or layers, because that's how these get hooked in, during different kinds of, or during different timings of the training loop. So for pre-forward hook, this generally could be useful for, say, moving layer weights to a particular device, or investigating input shapes as you're passing it to a model. layer weights to particular devices. Things that probably come to mind is big model inference, or using something like CPU offloading during distributed training with like deep speed or FSDP. For the forward hook, this would be you're trying to investigate the model shapes after they've gone through the forward pass. In my case, just today, I was dealing with the fact that certain layers in a model aren't divisible by 16. And so TorchAO's FP8 was giving me issues. So I was writing some debugging hooks to figure out what layers in my model were giving me troubles. These are why this is very powerful. On its own, it's great because you can do certain things, but really they're strong for debugging because you can sit there and go through and look at, okay, this is what this particular layer is getting. This is before, this is after. How is it different? Why is it giving me problems? And you can even make a hook that drops in a Python debugger, for instance, if you really wanted to go in deep, stepwise, hook it into a particular layer and go look at it. But getting a little ahead of myself there. Backward hooks, these would be things like monitoring gradient stats, so like checking for explosive gradients, making sure gradient clipping is happening as it should be. Interpretability of model outputs also generally is good. This is more of a forward hook, but also can happen during a backward hook. Introducing strong regularization before we fully apply backprop, and also monitoring gradient accumulation is another big one because we accumulate the gradients before we call backward, and that's sort of what backward hook is sort of good for. And then the last one is register hook on a tensor, which is when we want to do a specific tensor modification, not just layers, and also catching the intermediate activations of particular layers. Essentially, it's a more fine-grained forward hook when you think about it like that. This is a good place to check for questions, so let's see what we got. Dandon Power says, will the pre-forward hook be executed right before the layer's forward pass because this caused synchronization execution overhead, or can I set it to execute earlier before with forward pass? No, pre-forward pass is before the forward pass. Like right after it gets called, the forward happens. So when it comes to synchronization error issues, yes, generally you'd want to synchronize all of the, well, no. The forward pass, the pre-forward hook happens before the forward pass. Now you specifically bring up, could this cause synchronization execution overhead? If you're doing things right when it comes to sort of distributed data parallelism, zero and whatnot, each GPU should be acting as independent as it can for as long as possible. So the synchronization overhead is only as much as what you're running on independent GPUs, if that makes sense. So like if I have a pre-forward hook on every layer and it's sharded and distributed, each layer will have n amount of added synchronization because of the behavioral execution and how long that takes. Now, if we ran it, say, only on GPU-A's chunks of layers, then yeah, there's going to be an overlap between all of the other layers ran in, say, 50 milliseconds, and our added functionality runs in 100 milliseconds total for running it and the hook. Well, now we added a 50 millisecond per batch slowdown, essentially, because we still have to wait for it to finish before we can do everything else. Hopefully that answers your very good question. And then we have Rida asking, what is the difference between a hook and a certain behavior in the forward function of your module without gradient activations, of course? Nothing. What hooks give you, though, is a generalized model agnostic way to do it. So essentially, rather than needing to recreate the model source code from scratch to go pull down, say, Qwen3 from Hugging Face, and then modify it that way, and digging through the Hugging Face modeling code and copying and pasting, doing all that. Instead, we can just inject our custom behavior using a very simple function, which we'll look at in a little bit, and just go. There's no digging into source code. There's no figuring out certain behavioral issues. It's just find the layer we want to execute it on, add a hook, be done with it. Really good questions. Now, we're gonna create a very basic hook that goes through and during an execution of the model layers will tell us the input shapes and the output shapes. So here I have a very simple model, which is just nn linears followed by ReLUs, and they're a decent chunk of size to help with visualizing something later. We're going to be very simplistic and create a model that has essentially 3 fully connected, or I guess 4 fully connected layers, a 10, a 4, and 2 248s. And we have some example inputs and outputs here. Now, just to show that it works, and layers, this is what I get for changing the course material 2 seconds before we did things. Now we can just verify model X. Okay, great, it works. Now, let's go ahead and create a basic forward hook. Now, for some reason, my wonderful example has vanished on me, and I do not know why, but that's okay. We can deal with it. So when writing a hook, I'm going to do it as a class. So we'll say class my custom hook. It doesn't really need to take in inputs or anything. It's just going to be detailing things. So we're going to have our 3 different hooks that we want to visualize. Yeah, we'll do 3. So we'll say pre-forward hook. Now the pre-forward hook takes in a module, which is the layer it's being executed on, or we'll say the layer, the nn dot layer. And it takes an input because this is executed before the forward pass has actually done a thing. So we can say print layer module, say module dot class name, passing in input dot shape. And then we can define a forward hook, which gets called after the forward pass, which takes in a module, an input, and because it's after the forward pass, an output. So now we can say, we'll say pre-forward for, and then we'll say forward for. And then this is passed in because this and this are the same. And then we'll also specify an output. Also, technically, these are tuples, so I think we need to do input at 0 and output at 0. And also input at 0. All right, so first, let's just do a forward hook like so. Now, to register it, we need to add it to every single layer, right? So for us, I'm just going to copy paste for the sake of speed. We will create our class, hook equals my custom hook. And then for every module, this simply checks to make sure that the layer has layers. And if it does, then we will register the pre-forward hook, the forward hook, and go. Now, when I do model X, we should expect it to print a whole bunch of stuff. And let me go ahead and clean this up a bit. And we can see that we called the pre-forward hook, passing in the tensor size, 3210, which our input was, if we go back, 3210. That gave us an output of 2048 from our linear layer. Continued passing it in until eventually we get our output size of 4. Great. So now we know how to attach a hook to every single layer of our model, as well as be able to sort of debug how the tensor is going through the layers. Now, what if we also wanted to do a backward hook, right? That could be useful for showing us layer execution and how the layer shapes are going. Now, for the backward hook, the only thing that's annoying is the fact that I do not have the source code for the backward hook in order to remember what its inputs are. Let's go over to the PyTorch docs. We'll say backward hook. And register backward hook, which is technically full backward hook. And we can see here that it takes in module, grad input, grad output. So let's create that. Def full backward hook, which this is fun with PyTorch. They got rid of the backward hook and now call it full, which takes in the module, the grad input, and the grad output, which is basically the input and the output. So we can say input, grad. And then we can say backward, passed in input, passed in grad. And now if we go over to here, we can say backward equals module.register full backward hook. And we can say hook dot full backward hook. Now if we do output equals, and then we can just do a very quick loss real quick. And then we can call loss.backward. What do we got going on? Something is up with the fact that probably input is none. And we just have our grad. Also, we are making far too many of our model hooks. There we go. All right, so now if we go through the backward, we can see that we do chain rule properly, right? So we start at the last layer and its grad, and then go back up to the start of the model. So that, in a nutshell, is pre-forward hooks, forward hooks, and full backward hooks. So, as I said, useful for, say, moving layers between GPUs, or doing some sort of gradient accumulation, accumulating the gradients, modifying the gradients, and so forth. Any questions on that? Essentially, a hook is just a function which modifies either the input, the output, or the gradients that occur during training from a particular layer, set of layers, or a particular tensor module on a in a model. Why are input and outputs tuples? That is sort of, it's a generalized way because PyTorch doesn't know how the outputs of certain layers will be, right? Because people can write their own custom models that have different expectations and different groups of layers. It's a way to come up with a sort of generalized approach that will work for most people's models. What kind of use cases are there for an ML engineer to create their own hook functions? Generally, sort of like I brought up before, it's for debugging and visualizations, which is exactly what ChatGPT found for you, Mert. The biggest use case is that I can think of that is very, we'll say, basic, is heat maps for CNNs. Right? It's a great way for you to visualize, say, the last layer before we get to the linear layers on a fully connected CNN like ResNet, what the model was looking at. And you can hook that into every single layer if you wanted to. For full backward hook, is grad the same as pgrad? Yes, it should be. And then, so PyTorch hooks are closer to callbacks than to webhooks. Yes, exactly. Very good point. That is exactly the connection I wanted you to realize. They are not really webhooks. They are more so callbacks. Nicely done. All right. I am very happy with where we're getting. Cool. So does TensorBoard use hooks for the visualizations and layers? Yes, it does. Awesome. This is phenomenal. I love the fact that we're getting this. Okay, let's create a practical example. And rip off Hugging Face Accelerate. So we're going to think about how we would write. Well, okay, one last little thing. When we're all done with hooks, generally we clean it up by removing the hook. So if we looked earlier, I stored all the hooks in handles. The reason why this matters is if there's CUDA memory allocated for these, there's references to them and you can't quite clear CUDA out all the way. So in order to deal with that, for handle in handles, we can call handle.remove, which will essentially destroy the hook in whatever layer it is. So you don't have to go through and find what layer and remove it explicitly, though you can. Instead, we just keep track of all the hooks we made, remove them. Now, let's think about how we would do a very simplistic big model inference hook. First of all, we need to know what device we want to use, because essentially we're taking the input, right, a tensor that we'll say is on CUDA, and taking it to a layer that is on CPU, turning that layer from CPU to GPU, passing the input through it, and then keeping the output on CUDA, but removing the layer from GPU. So let's write in init device. And in this case, this would be CUDA. Now, because we're dealing with inputs that go before we pass it through the layer and after we pass it through the layer, we're going to want a pre-forward hook and a forward hook. Module and input. Now, we don't really care about input here because for this particular simplistic use case, we're assuming that input is already on CUDA. Also, I forgot to mention this at the start. The fully annotated notebook of this will be available later today or tomorrow, depending on when I fix a few things, such as the missing code that we have. It'll be sent out as an email to all of you. So, actually, Matei is having a wonderful conversation, and so I'm going to quickly bring that up with Mert. Another thing that hooks are very important for and very good for is distributed training, because you need to synchronize gradients between different layers, send layer inputs from A to B and B to A, as you're doing like pipeline parallelism. And so they can be implemented through hooks. For instance, in the course code that I'm working on right now, 02 technically can be implemented fully as a hook. Now I say can. The last implementation of FSDP in PyTorch was not done through hooks because hooks can have issues. But yeah, a lot of what's happening in Torch distributed can be done through hooks because you need it at these particular layers. And in chat, there's a very good explanation by Matei. The chat will be available with the recording. So feel free to go reread that and sort of digest it all. Now for our pre-forward hook, all we care about is moving the module to the device. So we can say module.toSelf.device. Now to help with our benchmarking, we're going to do torch.cuda.synchronize and torch.cuda.empty cache. This is to help us monitor sort of how CUDA memory gets used. It isn't necessarily needed for what we're doing. And then pre-forward hook expects us to return the input. So we'll return input. Now for our forward hook, this is going to be the module, the input, and the output. Well, if our pre-forward hook moved the layer to CUDA, then our forward hook should probably move it to CPU. So we'll do module.to CPU, and then call our torch CUDA synchronize again, and return the output. This, in a nutshell, is the core parts of Accelerate's big model inference. Now, there's a lot more funky stuff when it comes to the official version, because you deal with like the meta device and specific offloading of specific layers and dealing with a bunch of other stuff. But at the end of the day, it takes a model, takes its layer, moves it to the right device when you're ready to call it, and then moves it off of the device when you're done. So let's see it in action. We'll go ahead and create the model parameters. We'll use something a bit bigger. We'll say there's 20 layers, because that way it'll use a lot more memory. Let's see. Collapse all. There we go. That way we can monitor it a little bit better. And then we will go ahead and create our hooks. So we're going to say use CUDA 0. Same thing as before. Register our pre-forward and our forward hooks. Next, we move an input to CUDA. That way we don't have to deal with it ourselves. Just makes things easier for us. Now we can go ahead and measure the peak memory that it used. So what I'm doing here is resetting the peak memory stats. Torch CUDA will track memory usage over time, which is really useful for what we're doing here. Now, because this is inference, I don't care about gradients, so we're dropping that. And then we can see the maximum memory that was allocated during the forward pass, and then the maximum memory reserved. What you'll notice, max memory allocated, 25 megabytes. That's the size of our biggest layer. Reserved, though, was 38. Why? Well, the reason for that is as we add more layers onto CUDA, it's allocating more chunks because these aren't happening as like in-place substitutions, right? As a layer gets moved to CUDA, we need to make a new CUDA allocation for that layer. Accelerate does things a little bit better to make sure that doesn't happen, which is why what we'll see whenever we move it to the entire model to CUDA, max reserved winds up being the entire model anyways. But for right now, this is what we have going. Also, I think I want a bigger model for our visualizations, so let's do 200. Did I mess that up somewhere? Let's find out. Num layers. No, that should be right. That is far less than I think, unless that's the actual size of the largest layer, which would make sense. Okay, so there is our base case, right? And we can go ahead and time it to see how efficient it is. So we say with torch no grad output equals model X. And generally what we will find is this is going to wind up being slower than just doing things on CUDA because it's constantly taking the data to and from CUDA to CPU, specifically the layers. There's no overlapping in how that's done. And so it's going to be slower because moving things to CUDA, allocating that memory, and doing all that fun stuff is a very slow process when it comes to what PyTorch does. Now, let's look at what happens if we do the same with just the model on CUDA. And technically, let's bring this back, move model to CUDA here. That way it can be measured. And there we go. We can see that it is 6 gigs. So this was successfully offsetting the essentially max reserved is the size of our largest layer. Max allocated is the largest size of, well, max allocated is the largest layer, sorry. Max reserved is the size of the largest layer plus the input, which is why it's a little bit bigger between allocated and reserved. So we can see that it works, right? We successfully have 1/1000th of the memory size. But, of course, it comes at a cost. That cost generally being speed. 8 milliseconds versus 651. So big model inference lets you do inference, but at a cost of, it's going to take a bit more time because, again, we're moving layers to and from GPUs. This gets alleviated with things like pipeline parallelism and even just sequential not parallelism, but sequential inference, where, you know, we load a quarter of the model on GPU A, next quarter on B, C, and D, and then we just move the tensor from GPU A to GPU B, and then things get speed up a bit. So that's why, like, this is a lot slower than generally what you would normally see in the wild, but or even what Accelerate does, because it's a little bit more efficient in its algorithm. However, we wrote an entire hook that essentially recreates Hugging Face Accelerate's big model inference in 10 lines of code. And yeah, that's kind of the whole thing. There's an example sort of why these are useful, how they work, what they are, and they're a really powerful tool just for the basic MLE for debugging, because you can find problematic layers, drop in a debugger, go examine shape outputs, and see sort of why model layers are failing. And it's also great for behavior analysis and interpretability, because you can attach hooks to like the last layers of the model, analyze sort of the last activations, look at, you know, an NLP, what tokens were highlighted, for vision, looking at what chunks of the image were most interesting, we'll say. And then for training, it's also really good because we can sit there and monitor for explosive gradients throughout the layers of the network to sort of judge how model training is going, aside from just, well, loss is going down, but it's a little funky, right? Or looking at the entire grad norm of the model and going, well, okay, the entire grads are weird. Well, we can take those weird grads and directly look at, well, weird grads happen because of layer 20. Why? And so, you know, on its own, hooks are kind of cool, but they're an especially strong debugging tool to really take your engineering up a level when it comes to working with tricky models. So that is all I had prepared for today. What other questions do we have? Because we still have about 10 minutes. Let's see. We have a question about not following how hooks can communicate between each other, especially for distributed training use cases. The way hooks communicate through each other is by using distributed operations. My course will cover this extensively, but essentially, a hook is no different than executing a separate function when we think about it like in this big scheme. A hook is no different than if I ran a function after, say, I got the outputs, right? So let's say we have output equals model X, do some function. And then we'll do loss equals loss func, loss Y, or we'll say output Y, loss step backward. Realistically, it's no different than just running this if we're thinking about the forward hook, right? So if we want multi-node communication, it has to happen inside do some function. So if we want, say, to look at every tensor, there needs to be a gather there, right? In order for us to gather all the tensors into one place, which is a synchronous event. And so nothing finishes until this function gets done. Or we can asynchronously have hooks, say they're debugging hooks, where we call do some function, say GPU 0 sends tensors to everyone to verify that like model states are being aligned for distributed data parallelism. And so that's asynchronous. GPU-A doesn't need to worry about everyone else reaching that point. So we can go ahead and do the loss, and then we wait for it to sort of do things. So you need to stop and gather in the hook itself. Yes, the hook is simply a vehicle for us to investigate things. And you can do anything under the sun you want through that hook with model inputs and outputs. So if you wanted to look at all of the gradients between every single device and every single GPU on every node, you could do a gather operation and then sort of investigate them through there. That's will be slow. That's why we want them for debugging, because you're performing a distributed operation with a collection, and we want to minimize that as much as possible, but that is a use case. Hey, TensorSlayer, I've observed that hooks can perform certain mathematical actions on tensors, specifically in LLMs. Any hook strategies we should consider for such use cases? Not really. Try and keep everything in place as much as possible for efficiency and not duplicating memory, of course. But in general, you know, it's a callback, right? You apply functionality to certain layers, to certain outputs, and you go from there. The case of do you use hooks versus a separate function or modifying the model itself would essentially be sort of, can you customize the model architecture? Yes, do it. No, use a hook. Does what you need to target a specific layer? Yes, likely use hooks for the sake of simplicity. Is sort of how that tier list goes. Are there any production use cases using hooks that you would recommend me read? Yeah, accelerate. Whenever people are doing big model inference, it accelerates hooks. That's why I chose this example. You can go look at the accelerate documentation. There's a neat visualization of how the hooks work. I made it using mainim. But that is why it was sort of the core case. If we want to think about true production, pipeline parallelism uses hooks in some capacity because it needs to send inputs to specific layers from the prior layer and do so in parallel. Essentially this, but on a more complex scale. That is the biggest use case for sort of using these hooks, is to speed up parallel inference on large infrastructure for large models. So at the end of the day, these are what those sort of folks are likely using under the hood to serve these gigantic models at scale. To minimize the difference when offloading modules to CPU, can hooks be used to load the next layer onto GPU, getting it ready? Yeah, that's a fun one, and something that we've sort of thought about. Of well, okay, can you have a moving average set of weights where you calculate the time it takes for layers to get onloaded, load the weights, and then offload, and overlap that with the time it takes to run a group of inputs through? Mate had a conversation earlier about that. It's an interesting question to sort of alleviate the bottleneck, and I haven't explored that too much, just because studies and use cases that hasn't come up for me yet. Just because typically when I do stuff like that, I just use Llama CPP, do CPU offloading that way, and just have GPU go burr. But for education and also understanding how Transformers does things with their new model APIs when it comes to serving, it runs this under the hood. And so it's really good to understand this concept because it sort of gets you the idea of how this stuff works, why it works, and also the fact that, yeah, for the last year, you've actually been doing this. And at the end of the day, I guess all participants will contribute to Accelerate, and then we'll feel like cowboys. Yes, please. Help Mate out. Absolutely contribute. At the end of the day, 10x yourselves and understand why the tools work that you're using. Because it's a lot easier to explain the black box when you can also explain the behaviors the black box is doing to the people and your bosses that want to know how it works. Especially because this tech is how everyone does things nowadays. When it comes to inference, like the diffusion boom, when it came to, hey, I can run, vision generation models on a 1080 because the largest layer in the diffusion could fit on a 1080. Everything else was offloaded, inputs pass through, go back, and there you go. What Mate said right there is sort of, I left him to the trenches because I'm on leave doing this fun course. So, help him out when you can. But hopefully that answers all your questions and you guys can go sort of play with hooks for a while. I will say, if you're interested more in this topic, just to shill for a moment, I do have a course coming up, of course. That's fun. Where I'm going to be talking about all of these concepts. Lesson 1's going to talk about hooks a bit more in detail, just because that's important. Well, really lesson 2. Because we can write chunks of 0 with hooks, and so that's why that's going to matter. It's going to go a little bit more in depth and more applicable than just, hey, we did moving layers to weights, moving layers to devices. So because you guys are here, you're going to get some supplementary material when this is all done, as well as a discount code, just because I appreciate you guys coming and listening to me ramble for 45 minutes. Do you have an idea on the next topic, Slurm? I want to talk about Slurm. I need to figure out the best way to do so, which involves rebuilding my Pi-hole cluster and getting that all working. So if I can get that going in the next week, yes, Slurm will be the next topic. Otherwise, as I'm writing the material, I'll see if there's other supplementary things that would be good. There will be an email shortly after this with all the resources. I'll include the notebook later tonight after I fix it all, so keep an eye out for 2 to 3 emails. I don't like sending spammy emails, but that's just how Maven does things. So thank you for not putting me on mute in your email chain. I appreciate it. Thanks everyone for coming. See you guys next week.